Okay, so let's see what we're going to cover. We're definitely going to cover, I just want to make sure that we remember the basics of the central limit theorem and this idea that if we have a normal distribution, right, and this could be a population of people, and we know it has a certain shape, it has a bell-shaped curve. We know it's symmetrical, 50% of people below the mean, 50% of people above the mean. We know that that it has a certain basic distribution that we can describe in terms of standard deviations, so that if we are 2 standard deviations below the mean and 2 standard deviations above the mean, we actually capture 95% of the population, and so on and so forth. You guys remember what that's called, right? That's the empirical rule. We know that that's the case. We learned about the Z table, right? And that's a table where we can actually calculate, based on the number of standard deviation below or above the mean, what different areas are represented, or what proportion of the population, or what percentage of the population, or what probability of picking an individual from that part of the population might be, based on the Z table. The values, the number of standard deviations away from the mean, and the values that are reflected in the Z table. Okay, so now we then learned that if we took repeated samples from this distribution, that we would get a new distribution, right? So for instance, if we took repeated samples of size 25, this new distribution would probably have a mean that is equal to or similar to the mean in the general population. But in this case, this mean, I'm going to call it X bar for argument's sake, this mean is going to be the mean of many samples taken from this population, and just the averages of each sample being put into a new distribution. We know that even though the mean is the same, or approximates the mean of the population, that the width of this is going to be narrower, just because we're taking samples of 25 and averaging them and using them to create this distribution. So they're not going to be so many extreme values, very low or very big values, like there would be in the main population. And we know the relationship between these two, the variability, the standard deviation of this distribution of sample means, right? The standard deviation of this distribution of sample means, unlike the means being equal, well, the mean of the standard deviation of this is going to be equal to the standard deviation of the population, this group, over the square root of the sample size. Bigger sample size gets, the smaller is the standard deviation, the width of this distribution. And just to keep things straight, so that we don't have to keep calling it standard deviation, we call this value the standard error. The standard error is the standard deviation of repeated samples of that size sample, repeated mean samples of size 25, the means built into a new distribution. So, okay, so that's a fundamental concept. Standard error is equal to sigma over the square root of n. So let's think about that for a second. That tells us that as n becomes larger, the standard deviation of the distribution of the means of the samples becomes smaller. As n becomes smaller, this becomes larger, right? Less precise or larger, more variability. Okay, so that's an important relationship, and it's a square root relationship, right? So if n is, let's get a nice even number here. If let's see, 16, let me think of something. 10. Let's see, 25. If n is 625, right? Then the standard error is equal to a sigma over the square root of 625, which is equal to, what is that equal to? That's equal to, it's equal to sigma over 25. On the other hand, if n is 25, right? N is 25, then for that group, the standard deviation over the square root of 25 is equal to 5, right? So look at this interesting relationship we have here. Square root of this is 25, square root of this is 5, and so on and so forth. Okay, so we know that there's something going on here with this square root. In other words, if we want this to be narrower, right? If we want the sample distribution to be half the width, if we want to halve the width, we have to have a sample size 4 times as big, because when we find the square root of it, it's half. Okay, so at any rate, but you can worry about that later on. You can play around with that in your heads. Okay, so now we kind of discussed that for a second. Let's get a fresh piece of paper here. Hope I stated that correctly. But at any rate, you see that relationship is a square root. Okay, so now we can put this to work for us. And one of the ways that we can put this to work for us is we can calculate confidence intervals, because we know how samples distribute themselves. Now, if we want to calculate a confidence interval, for instance, and we have, for instance, a situation where we take a sample and the mean is equal to 100 and the sample size is equal to 64, right? And now we need to know, let's say I told you that sigma for the population, okay, standard deviation of the population is equal to 10. That's unusual. Normally you wouldn't know that. If I told you that, you would then know that the way samples are distributed in this situation is that the standard error is going to be equal to 10 over the square root of 64, which is going to be equal to 10 over 8, which is going to be equal to 1.25. So now you know that 95% of the outcomes that you would get if this just happened to catch the mean would be 2 standard deviations below and 2 standard deviations above where you found your approximate mean. Okay, so in other words, I can say with 95% confidence, okay, and I'm stretching the truth here a little bit, I understand that, but just to give us a kind of an outline understanding of this, that means that I can predict that my 95% confidence interval for the true population mean, for estimating what mu really is going to be X bar, the mean that I got from taking a sample of size 64, plus or minus 2 standard errors, minus 2 standard errors and plus 2 standard errors. Well, we know that one of the things we learned is that 2 was part of something that we called, remember what it was called? Right? That was the empirical rule. That was part of the empirical rule. It's an estimate. It really turns out it's 1.96 standard errors, right? Would give us 95% of the outcomes. Okay, so 1.96 times the standard error, plus or minus 1.96 times the standard error, would now give us a range within which we're 95% certain that the true population mean lies. So I could only do this with this 1.96 because I told you what the sigma was for the population. Remember, these are parameters. They represent the values for the population. Okay, we never know the mean. If we knew the mean, with the mean of the population, we wouldn't bother with X bar because we'd already know what we need to know. Sigma, there might be occasions, rare occasions, where you might know it or you might have enough information to at least estimate it pretty well. Okay, so in this case, it's going to be 100 plus or minus 1.96 times 1.25. Okay, now do what I say, not what I do. I'm going to just use 2 here, to just save time, but don't do that. Don't round until the very end, if at all. Okay, 2 times 1.25 is going to be 2.5, right? And in fact, what I'm going to do is I'm going to just call it 2.44 because I think it's probably going to be closer to that, right? So it's 100 plus or minus 2.44. Okay, so our confidence interval is going to be 102.44, again, an estimate. And on the lower end, it's going to be 97.6656. Okay, so we're 95% certain that the true population mean mu lies between these 2 numbers. This is a way for us to take all of our uncertainty and put it in a form where we have a useful way to understand how precisely we know the true population mean. we know we don't really know what it is. We think it's around 100, but we know with 95% certainty that it's between 97.56 and 102.44. And if I wanted to be 99% certain, you guys might remember, if you go back, you can remember that in that case, we need to be more standard errors. If we need to have a bigger range, we need to be further out from the mean. So in that case, we want to be 2.58 standard deviations out from the mean. So it's going to be, in that case, x bar plus or minus 2.58 times the standard error. Okay, and again, that would be 100 here, plus or minus 2.58 times 1.25. And you can see that's going to give you a wider range, justifying that higher level of confidence that you're going to capture that mean. Well, that makes some sense, right? We should be okay with that, I think. So you got to certainly get some questions on doing a couple of these, and also a little bit on interpretation. Okay, there's one little question, might be 3-point question or something like that, which really will test your understanding. Okay, and every semester, I get about maybe 2 or 3 people that like get it, and I think it might be multiple choice. So I'm hoping they're not getting it because of multiple choice, but it's a multiple choice question, and it's not actually a numerical answer. It tests your knowledge a little bit, but only a few points, only 3 points or so. Okay, so in addition to this, we also have a situation where we don't know the standard deviation of the population or the mean of the population. We don't know either one of those things. So we're completely adrift. The only way we understand that population is from our sample, from the sample that we take. Okay, so I might find that x bar is equal to 100. And the standard deviation of my sample, in other words, those numbers that I got in my sample, I'm going to say the sample size is 25. The standard deviation I got from my sample is equal to, let's say it's equal to 20. Right? A lot of variability in this particular sample. So I know that the mean approximates the mean of the population. I know the variability of the people in the sample, in other words, standard deviation, approximates sigma, but they're not going to be the same. They only approximate them. So now we've added uncertainty. Not only are we uncertain about the mean, how close it is to the true population mean, but now since we don't know sigma, we've added an extra level of uncertainty. So we have to deal with that. Okay, the way we deal with that is when we calculate our confidence interval, x bar plus or minus, I'm going to leave this part empty over here. Might have been 1.96. That's very lightly 1.96. Very lightly, barely see it. Times the standard error will be our 95% confidence interval. Right. Well, now I need a wider interval here because I don't know the true population standard deviation. I don't know really how spread out it is. I'm estimating that it's 20, but I don't know it for sure. Okay, that's based on the sample that I took. So now what we need to do is we need to use a different number here, a number that is based on something called the t distribution. And the t distribution is similar to the z distribution, right? A z distribution, 95% is represented by a z-score of minus 1.96 standard deviations to the left of the mean and plus 1.96 standard deviations to the right of the mean. With a t distribution, well, depending on the sample size, what happens is that we have more uncertainty. So actually our t distribution for a sample size of 25 might look something like this. It's more spread out. So 95% might be a bit further out from 1.96. It might be 2.1, might be 2.2. We need to reference the t-table to figure out what it is. And the thing is that for every different sample size, for a sample size of 100 would be a little bit closer to the normal distribution. For a sample size of 10, might be a little further out, right? So each different sample size has a different value for t, or the t that we're going to use for 95% confidence interval. And how do we know what that is? Well, we got to go to the t table. And I think I got a copy of the t table here. Let's see. That looks good. What do we got there? Yeah, there we go. That's a copy of the t table. And this t table, the way that we use the t table is we look for the degrees of freedom. Sample size is 25. In our case, that would mean that our degrees of freedom are 24. And I would go across here to 95% confidence, right? 24 to 2.064. So that is the value that we would need to use in place of 1.96, 2.064. Okay, so that's my t value. Had it been a sample size of 10, then we would have used 9 degrees of freedom, and we would have used 2.262. Had it been a sample size of 25, use 24 again, but we wanted 99% confidence interval, well, then it would be 2.797. See how that makes it wider so that we are more confident we make up for that extra uncertainty because we don't know what sigma is. Okay, so what would I get here? I get 100 plus or minus 2.064 times our standard error. And our standard error now, standard error is equal to, instead of sigma, it's the standard deviation over square root of n, which is equal to 20 over 5 is equal to 4 times 4. So this would be approximately 92 to 108 or so. Right? You'd work this out more exactly, of course. Okay, so that's why we need the t distribution. We need the t distribution because we don't know what sigma is. If we know what sigma is, we can just use 1.96 and 2.58, and as it happens, 1.64 for only 90% certainty, right? But we need that t distribution when we don't know what sigma is, and that's almost all of the time in real life. Okay, so let me stop for a moment and ask you, up until this point, are we okay with this? Do you guys feel comfortable with this? And of course, I know that in some cases, you're going to want to go back and play this again and kind of go over it and so on. Maybe look at some previous videos or something like that. But you see the situations where we use 1.96 and where we use the t-score and how to calculate the confidence interval. Okay, good. I think so too. I think we're in pretty good shape there. So now I'm going to throw a little bit of a curve here. And that is that we also use this for proportions, okay? So in other words, if I had a situation where I wanted to know there's a population of, I'm the owner of 211 good humor trucks, right? They still sell good humor, right? The ice cream and the trucks and so on and so forth, the little tricycles go around and stuff like that. I own 211 good humor trucks. And I say to myself, you know, I got a new flavor. I got, let's see, what sounds really, I have quinoa ice cream pops, right? I don't know if I can spell this, quinoa. I think that's right. Quinoa ice cream pops. And personally, to me, it sounds disgusting, but who knows? There may be people that want that, right? Want quinoa ice cream pops, right? So I want to know what percentage of my customers would like me to carry quinoa ice cream pops. Well, I got 211 trucks, and every one of them sells 500 bars of ice cream a day. So that's a lot of people that are buying ice cream. But you know, I decide I'm going to do a random sample of my customers. I'm going to sample. I'm going to take a big sample. I'm going to have each one of these 200 trucks take a sample of 5 people randomly that come up to the truck and ask them if we had quinoa ice cream pops. Would you would you eat that? Would you be interested in buying that? And they're going to do it kind of like they do at the airport, like for random searches and stuff like that. They probably have a chart somewhere with random numbers, and they say, okay, this is the 4th person after this guy, and then the next one is another 8 people, and the next one's the 2nd person, and so I have some sort of random number generator that tells them who gets searched and so who gets a more intense search. So I'm going to say, okay, yeah, we're going to use the same thing on the truck. And you got to take 5 of your customers and randomly sample them. And we're going to do 200 trucks. So I'm going to have a sample size of 1,000 people. Okay. So I'm only going to do this if the majority of people want to taste it or want quinoa ice cream pops, right? So I find out, okay, the sample size is 1,000. And I'm going to say to myself, okay, so I am going to say that out of the 1,000 people, 520 people say yes, that sounds like a good idea to them. And 480 of those people say no, sounds gross, right? So what proportion of our sample thinks that this would be a good idea? Well, the proportion of our sample is going to be 520 out of 1,000 people say they think that might be a good idea. So it looks like 52% of the people that I have here are likely to want to buy these quinoa pops. But I said to myself, I'm only going to do it if I know that the proportion that I'm 95% sure that the proportion of people is greater than 50%. In other words, it's greater than 0.50. Well, it sure looks like that from this example, right? But you never know. I might have, if I took another sample of 1,000 people, I might get 47% the next time, or I might get 56%. So I want to know if I can say with 95% certainty that this represents a majority view, that more than 50% of the people want to buy these pops. Okay, well, so now I have to create a confidence interval. So my confidence interval is going to be, and what we're after here is we're after what P is, what the true population proportion for the 500,000 people in Brooklyn that buy pops every day from that truck, from these trucks. Okay, so we want to know what that is. All we have, but the only way we can evaluate that is by looking at our sample. And notice I use P, it's like I use mu for the point estimate for the population, but then I use a P with a hat, P cap, to represent the sample proportion. So my confidence interval is going to be equal to P cap plus or minus. Okay, so now I got to decide whether to use T or Z. Well, whether you use T or 1.96. Most of the time, when you're dealing with proportions, you will be working with a very large sample size relative to when you're dealing with numbers and means, right? So for that reason, it's going to be so close to 1.96 that for the most part, you would just default to 1.96. So I'm going to do that, 1.96. I'm just going to use 1.96. And you can use that as a general rule, times my standard error. Well, now how do I calculate my standard error? I don't see a standard deviation here anywhere, anything like that. But we have a formula for standard error. Standard error is equal to the square root of P times 1 minus P over N. Again, bigger the sample size is, the smaller the standard error is. Smaller sample size is, the bigger standard error is. Smaller this is, the narrower the confidence interval. The bigger this is, the bigger the confidence interval. Okay, so standard error. So it's going to be equal to, well, I don't know what P is. So the only thing I can use substitute for P is to use 0.52. So the square root of 0.52 times 0.48 divided by 1,000 sample size. So now I'm going to go get my calculator. Okay, now I'm going to say 0.52 times 0.48 equals this divided by 1,000 equals this. Comes over to real small numbers, but notice this. When I have fractions, I take the square root, it gets bigger. Okay, it's going to be 0.0157. For our purposes, I'm going to call this 0.016. I would grab an extra decimal place for you, like 157 or 158 in this case, to make sure that you're okay on this. Because you don't want to just go 0.01. I'm going to say 0.02. look how you're off by 33% if you round this to 0.02. And that's even before you multiply it. Okay, so 0.016 I'll use, you should use another decimal place. 0.016. Okay, so 0.016 is my standard error. Okay, so P cap, well, P cap is 0.52 plus or minus 1.96 times 0.016, I think it was. So I'm going to make believe this is 2. Again, save time. You don't do that. Do what I say, not what I do. 0.52 plus or minus 2 times this would be 0.032, right? So what would that be? That would be, let's see, that would be a range of 3% on that, 0.55, 0.552, and subtracting that from 0.52 would be 0.49, let's see, 0.48 rather, 0.488, I believe. I get 2 carry the 1. Yeah, I think so. That looks right. So we may have gotten 0.52 as our proportion from our sample, but we're 95% certain that the true population proportion for all the people that are going to buy ice cream is between 48.8% and 55.2%. So given that my true population is between these two numbers with 95% certainty, can I say with 95% certainty, I can't write that, giving me a hard time. Okay, can I say with 95% certainty that my true population proportion is bigger than 50%? Can I say that with 95% certainty? Well, no, because it could be as low as 48.8% within that 95% confidence interval. So no, I really would have needed to have a value outside of this confidence interval to say that it's different than 50%. Right? So unfortunately, we didn't get that. So we don't know for sure that it's greater than 50%. Looks good, but we don't know for sure. So that's how I would handle a confidence interval using proportions. Are we okay with that? Get a little bit of feedback there. Okay. Okay. So now we get into dealing with when we have situations where we're comparing a sample to, we're comparing a couple of samples to one another. In other words, we're comparing two means, for argument's sake. Hang on just a sec. Okay, so let's give that a try. Let's compare two means. Or actually, before we compare two means, I am going to take a variation of that, and I'm going to say, let's compare a single mean. I'm going to open up something that's a little, let me see if I can't find this. Steps. Okay. Here's a listing of steps in hypothesis testing. And here's a file that I made up that you guys have seen called Ttest variations. Okay, so now we can have basically maybe 3 or 4 variations of the t-test. One variation of the t-test, remember the t-test compares the means of two groups. One variation of the t-test is when I have, say I got two populations, population 1 mean and population 2's mean. I say to myself, I want to compare the two of those, right? One situation could be, I know the mean of this population. Let's say I know that it's 90. But this one, I don't know the population, so I have to take a sample, right? And I got X bar, okay? And my X bar comes out to be 88, let's say. Well, now I have to say to myself, well, given the sample that I have, maybe the sample size 25, given the sample that I took, can I say with 95% certainty that this mean is different than this mean, when all I know is the mean of the sample that I took? And that is called a single sample t-test. Okay, so that's one variation. How would I do that anyway? Well, let's think about this. Let's say my sample size is 25. My standard deviation from this sample is equal to, let me make a number up, is equal to 25. Okay, going to give it a big variance. Okay, let's say that maybe it's too much. I want this to work at least reasonably well. Say my sample size, let's say my sample size is 9. My standard deviation is 9. Okay, so okay, I'm going to stick with that. Let's say my sample size, my standard deviation is 9. So now, in order to tell whether or not I can say with 95% certainty that these two values are different enough for me to say that I'm going to reject the idea that they're equal, and I'm going to say that they're unequal, right? I need to have those two means be far enough apart that that big a difference will only occur less than 5% of the time, right? That's called our p-value or significance. That extreme a difference would only occur less than 5% of the time. So you can use that as evidence to say, I can reject the idea that they're the same. Okay, so now how do I calculate that? Well, we need to calculate the difference between these two. And how do we do that? We take x bar minus mu, right? Single sample t, that's x bar 1 and mu that we know. Okay, so x bar is 88 minus mu, which is 90. That's the difference. And that comes out to be 2. But that doesn't really help me, does it? Because I don't know, whether that's a big difference or a small difference. However, what I can say is, well, how many standard errors apart is that? How many standard errors is that apart? And if it's more than 2 or 3 standard errors apart, gee, that's good evidence that you can say that they're different, right? Even though the 2 doesn't mean anything, the number of standard deviations. Actually, what I'm calculating here is the t-score, the calculated t-score that I need to tell how far apart these are in terms of numbers of standard errors. So what's my standard error going to be? Well, my standard error is going to be, it's going to be 20. I'm going to be 9 over the square root of 25, which is 9 over 25. That was a bad choice. I'm going to make it 10. 10 over 25, which is going to be, 10 over 25, 10 over 5 rather, square root of 25 is 5. That's going to be equal to 2. Okay, so, I'm going to go back and do this again. Hang on. Our standard deviation is equal to 5. Okay, so that's going to be 5 divided by the square root of 25. That's 5 over 5 is going to be equal to 1. Okay, so now I'm going to say to myself, okay, my standard error is equal to 1. So what is my t-value? How many t-scores apart? How many standard errors apart are these? It's 88 minus 90 over the standard error, which is equal to 1. Okay, and that's going to be equal to 2.0. Okay, well, it's 2 standard errors apart, 2 t-scores apart. Well, remember our t-distribution. We have to go to our t-distribution to figure out how far apart that we need to be to have a 95% confidence that that these two things are different from one another. Well, you might remember when I did that. Remember what the number was? I remember what the number was. I'm going to go back there and get it anyway to show you. Okay. Okay, 25, sample size 20, I have 24. So it was equal to 2.064. So in order for me to say with 95% certainty that they are different, I would need my t-value to be bigger than 2.064. We want them to be more than that distance apart in terms of standard errors. This number is called a critical value of t. Critical because that's the point, that's the measure that we're going to use to decide whether or not to reject the null hypothesis that these two are equal. So my calculated t-value is 2.0. Is my calculated value big enough for me to say that they're different? Are those two numbers far enough apart for me to satisfy the t-score that I need, the critical value? That's not a rhetorical question. I'm going to wait for you to answer it. No, they're not far enough, not quite, right? Not quite far enough apart. So I failed to reject my null hypothesis. I can't say that those two populations have different means, have different population means. Okay, well, let's take a look. What if this sample had been a sample size of 100? Okay, let's see how this might have worked out if this were a sample size of 100. Well, now my critical value, let's see, first of all, my standard error is going to be equal to 5 over the square root of 100, which is equal to 5 over 10 is equal to 1/2, is equal to 0.5. So my t score is going to be 88 minus 90 over 0.5. Okay, well, that's 2 over 0.5 is equal to 4.0. Okay, and not only that, but gee, look what happens to my t-test here. I can make it a little bit bigger. Look what happens to my t-test here. What happens to my t-test? Well, for 100, my critical value of t, it's hard for you to see, I know, 1.984, right? Because my sample size is bigger, my t-distribution is narrower. So it's not 1.96, but it's getting closer, 1.984. So now my critical value of t, which I need to exceed t critical, is equal to 1.984. Okay, so can I now say that the means are different from one another? Can I reject the null hypothesis now? Again, not a rhetorical question. Yeah, exactly. Now I can reject it because now I have enough evidence that this big a difference, 4 standard deviations apart, so 4 standard errors apart, is way more than I need to know that that's not going to happen more than 5% of the time. So I can reject my null hypothesis. And again, just as a quick statement, for the single sample t-test, your null hypothesis is mu1 is equal to mu2, and your alternative is mu1 is not equal to mu2. You're not going to use x bar because we always identify the population means, not the sample means, right? But however, little trick, since we know that this mu2 is equal to 90, we don't have to write that. We could just write mu1 is equal to 90, which we know to be true. Mu1 is equal to mu2 is the same thing as mu1 is equal to 90, because 90 is what mu2 is equal to. And down here, you could write mu1 is not equal to 90, like mu2. Right? So you could actually write it that way instead if you want. Either way would be okay. So, yeah, so that's a single sample t-test. Well, now things get a little more complicated because in real life, we are often comparing, we don't know the means or standard deviations of the two populations that we're comparing, right? So even though what we're really interested in is mu1 and mu2 and knowing whether they're equal or whether they're not equal, right? That's really what we're interested in, right? Okay, we don't know what mu is, but if we take a sample from each population, well, then we might find that x bar 1 is equal to 90, x bar 2 is equal to 100, and sample size here might be equal to 100, and I'm going to say 25, and sample size here might be equal to 25. Okay, did I say this was equal to 100? Let me think for a second. Okay, 100. I just want to think for one moment here. Okay, square root of 25 is 5. 5, 2, 2. I'm going to say that the standard deviation for this group here is equal to 4, and the standard deviation for this group here is equal to 6. Okay, so now I have something else. I have a 2-sample t-test. I'm going to compare the means of these two, and I'm going to want to know whether whether this t, the difference in number of standard errors, whether it's different enough for me to reject the null hypothesis. So what is t equal to? What's my calculated value t equal to? It's equal to x bar 1 minus x bar 2 over the standard error. Okay, well, okay, well, how do I do here? That's 90 minus 100 over the standard error. How to calculate standard error? Well, standard error is equal to, what was it equal to again? It was, if we knew it, it would have been equal to sigma over the square root of n. But if we knew standard deviation, it would have been standard deviation over the square root of n. Then we use a t. But wait a second. I have two standard deviations. Which one do I use? And I got two sample sizes. Which one do I use? Right? So now we have to take another approach to this. Okay, so now this is a two-sample t-test, right? Also called an independent samples t-test. Independent samples t-test, right? So we now have to deal with all of these issues about which standard deviation do we use, how do we interpret the degrees of freedom for the sample sizes, and so on and so forth when I have a sample from each population and so on. Well, first of all, there's two possibilities here. One possibility is that the standard deviations are equal or approximately equal, and the other one is that they're different. Standard deviation 2 is different from one another. And usually, informally, if we see that the standard deviation of one group is not double the standard deviation of the other group, we say that they're the same or similar. Okay, so we'll stick with that. But if one is more than double the other, if this has been 4 and this 10, we would have said that the standard deviations are unequal, right? So we really have two kinds of two-sample t-tests. We have one with equal variance or standard deviation, and we have one with unequal variance or standard deviation. Well, how do we handle that? Okay, the way we handle that is in that document that we had from class. Let me open that up again. Let's see, t-test variations. There we go, here it is. Okay, make that a little bit bigger. Good. Let's see how this works. Okay, so this formula, this is for standard deviations, or when the standard deviations are assumed to be equal. That's the case we have here, right? We've decided that 4 and 6, that's close enough, we call it equal, right? So what do we have to do here? Well, here's the real money calculation here. T is equal to the difference in the two means divided by the standard error. But now look how complicated that standard error is. First, you have to calculate something called SPSS, pooled standard deviation. And then you have to multiply by the square root of 1 over the sample size 1 plus 1 over the sample size 2, right? That's another kind of thing that's getting in the way here. So what is the pooled standard deviation? Well, the pooled standard deviation you have to calculate first, and that's equal to sample size 1 minus 1, 24, times the standard deviation squared, which was 4, squared is 16. 25 minus 1 is 24, times 6 squared is 36, over 25 plus 25 minus 2 over 48. So once you've calculated all that, taking the square root of it, then you use that pooled standard deviation down here in this formula. And you multiply by the square root of 1 over 25 plus 1 over 25. In this case, that would be equal, so that'd be 2 over 25, which is, I guess, 0.08. 2 over 25, same as 4 over 100, right? 0.08, right? 8 over 100, 0.08, square root of 0.08, whatever that comes out to, times pooled standard deviation is what your standard error is, and divide that into the difference between these two, which is 90 minus 100, which is 10. Okay, and that would give you your t-score. And what would you do then? Well, then you would go to the t-table. But wait a second, what degrees of freedom am I going to use on the t-table? Well, your degrees of freedom are going to be the sum of the two sample sizes, 25, 25, minus 2, which would be 50 minus 2 is 48. So you would use, as close as you can come to 48, I'll use 50, you would use 2.009 as your critical value of t to compare this result to decide whether you can reject the null hypothesis. Wow, I'm sweating. That was a lot of work, right? And that's nothing. Wait till you see what we're going to do with the unequal variances. That was a ton of work. But you could do this. I mean, it's tedious, but it's just a matter of plugging numbers in and then doing the calculations, right? And as long as the calculated t is bigger in this case than 2.009, I think it was, or something like that, it's bigger than the critical value t, you can reject the null hypothesis that mean 1 is equal to mean 2, and accept the alternative, the mean 1 does not equal mean 2 in the two populations. That's what it looks like when we do a calculation involving unequal variances. Involving equal variances. Well, what about if the variances are not equal? Well, I got the same formula here. Again, you can recognize this. On top is the difference between the two means. On the bottom is the standard error. So the t is equal to the number of standard errors here. Right? So if this were 10 over 2, this would be 5 standard errors here. Okay? So now we calculate this a little bit differently. This would be if this had been 4 and 10, the standard deviations, and we assume unequal variances, this would be 16, and this would be 100 divided by 25, divided by 25. We work that out and add them together, take the square root of it to get our standard error. And then the top would be 90 minus 100, which would be 10 divided by whatever comes out down here, and that would be our critical value of t. Wait a second, what is our critical? That would be our calculated value of t. But what is the critical value of t that we're going to use to compare it to? Well, when we use equal variances, that critical value was just the 25 and 25 minus 2 for the two groups was 48. But in this case, unequal variances, we can't do that. This is our formula for degrees of freedom. Wow, there's a mouthful there, right? Okay, so I can't even read the thing. It'll take me an hour to read this thing, right? So actually, in practice, if you're just doing it quickly, you might just take the smaller sample, subtract 1, and use that to find your degrees of freedom. It's very conservative approach to that. You know it's going to be bigger than that for sure, but this is an easy way to get past this. Okay, in reality, most of this stuff in real life, you are going to be using SPSS to calculate, or SAS, or R, or some other statistical program. Okay, so that is how we deal with unequal variances when we do a t-test. Okay, well, what else we got? Well, we got proportions. You have two proportions. Oh, this population, 10% of the population here is diabetic, and 12% of the population here is diabetic, based on a sample size of 500 from this group and 1,500 from this group. So we have two sample sizes, and we have two proportions. Okay, well, how do we figure out what the value is there? Well, first of all, number one, our critical value is going to be 1.96, because we're always dealing with large samples in this case. Critical value is going to be 1.96. So we're not going to calculate a z-score to compare to it. We're going to be comparing to a t-score. We're going to be comparing to a z-score instead. So let's calculate that. Again, it's the difference between the 2 point estimates over the standard error. So even though it looks different, you're doing the same thing. The sample proportion 1, which I said was 10%, and sample proportion 2, which is, I think I said was 12%. Okay, so that's maybe 2% on the top. And then down here, we're going to just simply fill in each of these. Oh, excuse me. Then on the bottom, you're going to use the pooled proportion. And what's the pooled proportion? The pooled proportion, see this P doesn't have a 1 in front of it or 2, is P1 times N1 plus P2 times N2 divided by the sum of the two sample sizes. In this case, I think what we say was it was 2,000 or something like that. Okay, so this is basically a weighted average of the two proportions. Okay, so you would calculate your pooled proportion here and use it down here to calculate your standard error, divide this into that, and now your only concern is it greater than my critical value of z, not t, z, but big sample, very big sample. And Z, we know, is 1.96. So if this calculated Z-score comes out to be bigger than 1.96, you would reject the null hypothesis. And what would the null hypothesis be in this case? In this case, the null hypothesis would be P cap 1 is, excuse me, I made a mistake. I keep telling you not to make right there, right? We're only in the hypothesis, we're always talking about the population needs and proportion. So my null hypothesis is the proportion of people who have diabetes in population 1 is equal to the proportion of people who have diabetes in population 2. And my alternative hypothesis is that proportion 1 without the cap is not equal to proportion 2 without the cap. Right, so that would be my null alternative hypothesis. And if this came out to be 2.15, we would reject the null hypothesis, accept the alternative. If this came out to be 1.91, we would fail to reject the null hypothesis, right? Because it's under that 1.96. Okay, so that's really what we're dealing with here. Except we're not going to do it with this. We're going to most likely be doing it. You might be asked to do a single sample Ttest, because that one's really simple. I know we just did that. That one is really simple. But on an exam, you probably, if we're going to wind up looking at Ttest, independent Ttest, you're probably going to use SPSS. And in fact, we had from class, we had a couple of examples of that. Here is a 2-sample Ttest. I'm going to open that up in SPSS. Okay, and SPSS, of course, is going to take 20 minutes to open up. Should open it up before. I should open it up while I was talking. Is it bouncing? I see a little dot underneath it. Not bouncing though. I'm reluctant to hit it. Oh, there it goes. I don't want to hit it again because I get, there's 3 versions of it. While this is opening up, any questions so far? You're either stunned or you're feeling pretty good. One or the other. I can't tell because I can't see your faces. So if we were doing brick and mortar class, I'd be able to see your faces and I would be able to tell almost immediately. Okay, so here's a situation where we have males and females and they take some sort of performance test or something like that, or physical test or a blood test or whatever, and we want to know whether the mean value for females is different than the mean for males. Okay, well, one of the things I need to know is, okay, what is the mean for males and the mean for females, and what are their standard deviations? So I'm going to go up here to Analyze. I'm going to go to Descriptive Specifics, Explore, because I want to evaluate this separately for males and females. I'm going to put the values. A numerical variable always goes into the dependence list. And the categorical variable, in this case gender, goes into the factor list. And I'm going to ask SPSS to give me an idea of what the means and standard deviations are for these populations, for these 2 groups. Let's take a look. The mean for females is 10. The mean for males is 7.56. And the standard deviation is 2.7 for females. And for males, it is 1.9. So is one of those more than double the other? 1.9 and 2.7. Well, no, they're not. So I'm going to assume equal variances. And if I'm going to do it by hand, I would use that first test for doing the t-score using equal variances. But now I'm going to use SPSS to solve this. I say to Analyze, what am I doing? I'm comparing means. And I'm going to move over here to, let's see which of this is not a 1-sample t-test. It's an independent samples t-test. So again, I'm going to move the test variable in there, the gender variable in here. Now, dirty little secret, SPSS is going to ask us to tell it what numbers represent male and female. I don't remember, so I'm going to guess. Because I don't want to close this right now and go back into it. I'm going to guess it's 1 or 2. See if I got lucky. Then I'll say, okay, I think I got lucky. Oh, look at today, bar graph, bar chart for us. And look, it looks like they're quite different males and females. But it's a really small sample size. So let's take a closer look. Okay, so now I'm going to go down here, and notice that there's a tall line over here, very difficult to see, at low resolution or over the internet. But there's a line here right under the eye. It goes down like this, under the eye and independent. It goes down like this. It separates this to the left and right. Okay, the t-test begins here, starts here and goes to the right. But before that, on the left-hand side, is something called the Wien's test for equality of variances. And this is a test. Turns out that the value, the statistic value, the statistic is called F, not related to analysis of variance, just happens to use F also. Right? So the F value is 1.456, and the significance is 0.245. That's the probability of getting at least this extreme of value if the variances are unequal. In other words, kind of like our null hypothesis. Our null hypothesis is equal variances are assumed, and we're only going to reject that idea if this is less than 0.05. So if this is greater than 0.05, we're going to stick with the top row, which says equal variances assumed. If this is less than 0.05, we're going to go with the bottom row. Often it won't make much of a difference, but we're going to use that convention. So now I'm going to stick with the top row. I'm going to cross here. The t-value is 2.184. Well, now the t-value, that's very interesting, but the question now becomes, is that t-value large enough to reject the null hypothesis? And we know for equal variances assumed, we just add the two samples together, which are 9 and 9 is 18, subtract to 16 degrees of freedom. Let me go over here to degrees of freedom. The critical value of t for 16 degrees of freedom is 2.12, and our t-score was 2.18. 2.18, 2.12, I've exceeded my critical value, so I can reject my null hypothesis. Well, SPSS takes this a step further. Okay, it looks 2.18, 16 degrees of freedom. I'm going to calculate not just that it's less than 5% chance of being wrong, I'm going to calculate exactly what the probability is of being wrong. And it calculates it and figures it out and says it's 4.4%. As long as that significance, that p-value, that probability of getting that extreme of value if the null hypothesis is true, or in other words, of being wrong if we reject the null hypothesis, is less than 5%. So the critical value, exceeding the critical value of t, and this being less than 5%, both are indications to us that we can reject the null hypothesis. Okay, but now look, what if I assume equal variances, not assume? Well, we would have still gotten 2.184 also, but we would have gotten a different degrees of freedom. And notice, remember how complicated that formula was for degrees of freedom for unequal variances? It wasn't just n1 plus n2 minus 2. It's a weird formula. And look, we got a weird result for that. And SPSS was able to do that, get that, and still calculate a significance for us. And we still would have rejected anyway, even if we made the mistake of going with the bottom row. So that's an example of equal variances. Let's take a look at an example of unequal variances. I don't know where SPSS went there. I'm double clicking on this anyway. So we'll have to wait for it to open again. Let's take a look at unequal variances. Okay, hopefully it opens with the data. Here we go. And my license is going to expire. There we go. Okay, so this time, things are a little bit different here. Let's do this analysis. Analyze, I hope I got the right one. Compare means, again, it's independent samples. Okay, let's go ahead and do our test. Gender, Okay, define our groups, 1 and 2. This could be 1 and 0 and 1 on occasion, and so on. Okay, give me a hard time here. Let me try this again. 1 and 2. Okay, it could be 0 and 1. It depends on your particular situation. And I'm going to click OK. Depends on how you're coded. Right? Like in other words, here you can see that if I turn off the value labels, right, you can see that male and female are represented by 1 and 2. If you go to the variable view, you can see that gender, by clicking values, 1 equals female, 2 equals male. Okay, so let's go back to this. Let's see my output. Where did my output go? Okay, that's my output goes up. Oh, nope, I lost it. There we go. Okay, so let's take a look at this Levine's test for quality of variances. Well, first of all, this is 10 and this is 7.56. The means are approximately the same. But look, the standard deviation for female is 2.7. Standard deviation for male is 1. Right? Well, that's more than one is more than double the other. So in this case, I would use the formulas for unequal variances. Okay, well, how does that unpack this down here? Well, what did the SPSS find? Well, SPSS found equal variances assumed the significance value, the p-value for that is 0.013. It's less than 0.05. So that means you can reject the idea, the null hypothesis, equal variances assumed, and use the lower line, equal variances not assumed. And the t-value turns out to 2.5. Our degrees of freedom are 10.1, and we can look up degrees of freedom 10. And you'll find that the t-value, critical value t is less than 2.5, so it will allow us to reject the null hypothesis. And the probability would be wrong if we reject the null hypothesis is, again, less than 5%. So again, I get to reject the null hypothesis. Well, now your question might be, well, what if you want to compare, what is that single sample t-test? How do you use this for a single sample t-test? Well, a single sample t-test, I go on places. In a single sample t-test, you only have a sample for one of the two populations. Here's a sample for one of the two populations. Okay, let's see what our sample looks like. Analyze, descriptive statistics, descriptives, and just going to go for really simple stuff. The mean and the standard deviation of our sample. And our mean was 9.89 with a standard deviation of roughly 3. Okay, it's a small sample too, it's only sample size 9. So I'm going to say to myself, okay, let's see. The mean is 9.89. I want to see if this mean for my sample group is equal to or not equal to a known mean for a population. Remember, this is just X bar. A known mean for a population, which is equal to 12. Okay, so my null hypothesis is mu1 is equal to mu2. Mu2 in this case is going to be 12, right? Mu1 is represented by my estimate, the X bar. And mu2 is not equal, and mu1 is not equal to 12 is our alternative hypothesis, or mu1 is not equal to mu2. Okay, so I'm going to go analyze, compare means. This time it's a single sample t-test. And again, we only have one sample put in here. And then we're going to compare it to the known population mean of the other group. That's our test variable. That's our test value. That's where we put in the mean of the other group. Click OK, and SPSS very quickly calculates. Notice that's only single sample test, so there's no question of equal variances or not. And the t-value is 2.15, and the probability of being wrong if we reject the null hypothesis is 0.063. Anyone want to hazard a guess? Can I reject the null hypothesis now? Again, not a rhetorical question. I'll wait. No, you can't. Thank you very much. No, you can't. Exactly right, because this is not less than 0.05. If this were less than 0.05, that would indicate there's less than a 5% chance that our sample mean is from a population that that would be that far away from our known mean of 12. But that distance would be so big that would only happen less than 5% of the time. In this case, it could happen 6% of the time. So we can't reject the null hypothesis. The submit p-value is not less than 5%. Okay, we have a too large a chance of being incorrect if we reject the null hypothesis. Okay, so what about paired sample t-test? Paired sample t-test, that's a kind of unique thing, right? We've looked at that in class. And let's take a quick look at it here. Open data. And here's our paired samples t-test. And in this case, we have two sets of data, except that we're comparing two populations or two numbers side by side. In this case, each subject here, line represents a subject. Each subject has taken the same test, has taken a placebo and been tested, has taken a drug and been tested, placebo and drug, placebo and drug. So now we're not so interested in what the average was for the placebo, what the average was for the drug. We're interested in how different was it for each one of the placebo and drug in the same person. So we actually could just take this and this, subtract them, and get a new column here, which gives you the differences between the placebo and the drug. So if the drug and the placebo have the same effect, have no effect, right? What would you expect to see here? Well, you would expect to see here no difference in the patient number one between placebo and drug, is zero difference, right? Or maybe a small negative difference or a small positive difference. But then this one you might see a small negative difference, this one a small negative difference, this one a small positive difference, this one a small negative difference. So we're not going to get always the same result, but on the average, some of these would be negative, some of these would be positive. If the placebo and the drug have the same effect, if there's no difference, then we would expect the means of the differences to be equal to zero. So that's our null hypothesis. The mean difference between the placebo and the drug is equal to zero. Okay, and since I only have one column to compare to a known value, zero, in other words, mean difference is equal to zero is our null hypothesis. Mean difference is not equal to zero is our alternative hypothesis. This is just really just another kind of a single sample t-test, except that we're always going to set it equal to zero. We're going to analyze, I'm going to compare means, and we can use one sample t-test on here if we calculate, if we made another column with the differences. We have another way, we just can go right down here. Okay, and in this, it's going to wait for me to tell it both values, placebo and drug, right, compared to one another. Okay, and before, let me click OK. Click OK. And here is our result and our t-test. Our mean, the value of our mean is 1.556, the mean difference. Is that different enough from zero for me to be able to say that the mean difference is not equal to zero, rejecting the hypothesis? Well, let's see what our t-score is. Our t-score is 1.730, 8 degrees of freedom. That represents a probability of being wrong if we reject the null hypothesis of 12%. So our t-test tells us we don't have enough information to reject the null hypothesis and say that even though the difference was 1.5, to say that it's really different from zero with less than 5% chance of being wrong. So we fail to reject the null hypothesis. Okay, so we come now to our biggest challenge now, which is analysis of variance. Actually, it's really not that big a challenge. Okay, so I'm going to see if I can find a good example of this. Let me see if I have something here that you haven't seen before. Oops. Let's see. There you Let me just get a .sav. And I have something here, maybe just a note for .sav. Maybe I can come up with a quick file that you haven't seen. Nope, that's it. Okay, here's something. I don't know if you've seen that before. Oh, that might be from an exam. Yeah, I don't want to play around with that. I don't want to get that wrong. Okay, well, I'll tell you what. Even if it is from an exam, I'm going to open it up. And I'm just going to change the numbers. Okay, let's see. I have a question here. Using it, what Ttest would you use to test the groups of 3 to find the answer? We're about to do that. We're not going to use the Ttest. We're going to use analysis of variance instead. And we're going to, it's kind of a little hidden in there. So we're going to figure out where to find it. So I'm going to open up this file. I don't know what that is over there. I don't think it liked that data. Let's see. Okay, whatever that means. Go away. Now, okay, I'm going to do this. I'm going to do a different file. Say open data. Let's see. I'm going to open this one. We'll open our birth data. Okay. I don't know what that's now. Okay, let's get this out of the way. All right, let's see what we have here. We have the birth weight of infants. This is 800 people, 800 births in ounces, and we have it in grams. And let's see what we have that has more than one categorical variable. Has more than one value. Okay, ounces, grams, for mature smokers. Race of the mother. Let's see. Yeah. Boy, SPSS really is not properly in here. Okay, here we go. Actually, this is gonna be, there's some of these gonna be very, either no people in the group or something like that. So I need to find something else. Morality, weeks. Yeah, let's see. I'm going to put that again. No, this is not so. Ethnicity of the mother. Yeah, I think this is a data set we made because it's a little bit simpler. Okay, so we have in this last variable, ethnicity of the mother, we have 4 groups in here. We have non-Hispanic white, non-Hispanic black, Hispanic, and other. Okay, and we created this because the 8 groups that we had under the race of the mother, right? Some of them only have 1 person or no people in it, so kind of made for a very sloppy table that we produced. So now we're just looking at these 4 groups, and everybody falls into one of these 4 groups. If they don't fall into anything else, they fall into other, I presume. Okay, so those are the 4 groups that we're interested in comparing. We want to know if there's a difference in the birth weight, our numerical variable, ounces, T ounces, ounces at birth, right, of baby at birth. Is there a difference within these 4 ethnic groups in North Carolina in this year? We want it in this particular year. So we want to compare those 4 means. So we want to compare the mean for non-Hispanic whites, the mean for non-Hispanic black mothers, mean for Hispanic mothers, and mean for all the other groups, mothers. Okay, we want to compare those four means. I could use a t-test. Compare the non-Hispanic whites to non-Hispanic blacks first using a t-test, then non-Hispanic white to Hispanic using a t-test. You can see how inefficient that is and how inaccurate that could be, right? So we're instead going to use analysis of variance. So I'm going to go up here to analyze, and I'm going to go into, well, what am I doing here? Even though it's called analysis of variance, I'm comparing the means of four different groups. What's my null hypothesis here? My null hypothesis is the mean for group 1 is equal to the mean for group 2, is equal to the mean for group 3, is equal to the mean for group 4. Mean of non-Hispanic white mothers is equal to the birth weight of the non-Hispanic white mothers is equal to mean birth weight for non-Hispanic black mothers, equal to mean birth weight for non-Hispanic mothers is equal to the mean for other mothers, right? So that's our null hypothesis. Our alternative hypothesis for the analysis of variance is that at least two of those means are different. Doesn't have to be all of them, just at least two of them are different. We'll worry about which two later. But right now, we just want to be able to demonstrate at least two of them are different from one another. So I'm comparing means. So I know that if I'm comparing means, it makes sense. Analyze, compare means. Just like our one sample t-test, independent sample t-test, pair sample, there's our analysis of variance right there. Repeat the null hypothesis. The null hypothesis is mu1, the mean for group 1, non-Hispanic white mothers, is equal to the mean for group B, which is non-Hispanic black mothers, is equal to the mean for Hispanic mothers, is equal to the mean for all other mothers. That's the mean birth weight. Right? That's the numerical variable here is the birth weight. Categorical variable is their ethnicity. Right? Those four groups. So, and the alternative hypothesis is at least two of those means are different from one another. Let me just write it down. Since that question came up, oops. Okay. So our null hypothesis is mu1 is equal to mu2 is equal to mu3 is equal to mu4. In other words, all the means are equal. And my alternative hypothesis is at least two means are different. Okay, we don't care which ones at this point. Could be that one is different than 3 or 2 is different than 3. In other words, mean for non-Hispanic white is different from others, or others are different from Hispanic, and we don't care which two are different, only that at least two of them are different. Okay, so let me go back to SP here, and let's actually do this analysis. Analyze, and we're comparing means, so that's where we would expect to find the analysis of variance. Even though you had word variances in there, you're actually comparing the means. So we want to get the weight of the child. I'm going to use ounces. You can use either. And we're going to break that up, factor that up into four groups. And those four groups are this last variable, ethnicity. That goes in there. So with the four groups, I don't have to bother to tell SPSS what the numbers are. It'll pick it up on its own. Okay, so now notice that there's stuff over here I'm not taking advantage of yet. First thing I need to do is find out whether I can reject the null hypothesis. If I can't reject the null hypothesis, we're done. In other words, we failed to reject the null hypothesis, done, complete, problem's over. So I'll click OK, see what our result is. Okay. So let's see what I wind up with. Okay, so we did this in class, and we did there's the videos for analysis of variance that you could go over, and you could look at where there's a sum of squares between the groups, sum of squares within the groups. And that comes from a calculation of the differences between the means at each individual value. And just like you would calculate sum of squares when we first week we did the semester, and then you divide by the degrees of freedom. There's four groups here, so degrees of freedom is 3. We take that number divided by 3. We get mean squares between the groups. That's the differences between the means. Mean squares within the group, how variables, how different are the weights within each group, Hispanic and white individually within that group. And that degrees of freedom is 796, which is 800 minus 799 minus 4, right? 3, I guess, okay, which is this number divided by degrees of freedom. The mean squares, the mean sum of squares within the groups is this number. And the F value, the statistic value, is the mean sum of squares between the groups divided mean sum of squares within the groups. So you want this to be a small number and this to be a big number. You want a big difference between the means, but a small variability within each group makes it easier to demonstrate this. Turns out the F-score is equal to 8.22. We could actually look up to see if that critical value for the F-score. More often than not, you'll be using SPSS for it. So now that we've determined that, what's the probability, given that big a result for the F-score, that we would be wrong if we reject the null hypothesis? Well, let's take a look at the p-value or significance. It's way below 0.05. It's actually below, it's less than 0.001. It's not really zero, it's less than 0.001. So we would say to ourselves, oh, it's less than, okay, that's so low that it's very unlikely that I would be wrong in rejecting the null hypothesis. So that tells us we can reject the null hypothesis. And what was that? I can reject the idea that all of the means are different and say at least two of the means are different. Have we decided which two of the means are different? No, right? So what does that bring to mind? That brings to mind now I have to figure out which of these two means, exactly, post hoc, which of these two means are different, right? So I need to go back and reanalyze this. Now remember, if this had been more than 0.05, I would have been done. I don't do any post hoc tests because more than 0.05 says I'd be making, I have more than a 5% chance of being wrong if I say that the means are different and then go do post hoc tests, right? So even if the post hoc tests happen to come out that it looks like one of them, a couple of them are different, it's not really official. You really can't go beyond this. This is not less than 0.05, stop here. If it's less than 0.05, then continue along. Analyze and compare means, one-way analysis of variance. Now this time, I already know what my result is going to be regarding my null hypothesis. Now I can go into post hoc or after the fact test. Once we've shown that the analysis of variance probability is less than 0.05, now we can go in here and we can choose one of the various tests that we can use to look at each one of the different comparisons. Mean 1 to mean 2, mean 1 to mean 3, mean 1 to mean 4, mean 2 to mean 3, mean 2 to mean 4, mean 3 to mean 4, right? So you do them all individually and take a look at each one of them. I would suggest for our purposes use Bonferroni or Tukey. Right? I don't think you'll ever wind up a situation within our class where you're likely to get a different result, significantly different result. Yes, so Bonferroni is what I say, a conservative, general use version of this. There's each one of these other ones has advantages in certain situations. It's preferable in certain situations. For the most part, we're going to use either Bonferroni or Tukey. So I use Bonferroni. Sounds like a nice Italian name. Sounds like some kind of pasta or something like that, right? So Bonferroni, like Ronzoni, Bonferroni. But at any rate, I diverge again. So let's see. I'm going to click OK. And now we will get the F-scores run again. See if it did it again, right? The F values run again, significance run again. But now look, now we get another table which gives us multiple comparisons for each of the different groups. So you'll notice that it duplicates its efforts. Non-Hispanic white versus non-Hispanic black. It does it here again, non-Hispanic black versus white. That's the same calculation, right? The two is just reversed, right? And you would expect to get the same result. And in fact, look, the significance is very large, 0.00, less than 0.05. So you can say with less than 5% chance of being wrong that the mean birth weight for non-Hispanic white, non-Hispanic blacks is different. Reject the null hypothesis that they're saying. Well, how about non-Hispanic blacks and non-Hispanic whites? So that's the same thing, right? Just you reverse it to them. So you do get the same result there, the significance same. How about non-Hispanic whites versus Hispanics? Well, no, that's not less than 0.05. I can't say that they're different. How about non-Hispanic whites compared to other? Well, there again, I can't say that they're different. Okay, how about non-Hispanic blacks to Hispanics? Well, it's 0.064. It's close, but you can't say, oh, I'm sorry, non-Hispanic blacks to non-Hispanic whites, non-Hispanic blacks to Hispanics is 0.019. You can say that they are different, that the average birth rate for non-Hispanic blacks is different than for Hispanics, okay, Hispanic mothers in this population. And how about non-Hispanic blacks versus others? Well, that's 0.064. You can't say that they're different with less than a 5% chance of being wrong, right? Because it came up 3.06. And so they just get duplicated down here. So this is the table you would use to determine which of these means are significant for these groups are significantly different. Assuming that the p-value is 0.5 different. Do we reject or fail? Well, the p-value is what tells you whether or not you can reject the null hypothesis. Is that p-value less than 0.05? No, it's not. So you fail to reject the null hypothesis. You can't reject if it's an analysis of variance, you can't reject the null hypothesis that mu1 is equal to mu2 is equal to mu3 is equal to mu4, et cetera, et cetera. Okay, and you could almost tell that, couldn't you? Because look how small the f value is. We want a big f value. This is tiny, right? 1.2 is tiny. So you should not be surprised that this p-value would come out to be so small. The significance, remember, significance of p-value on SPSS are pretty much interchangeable. Okay, all right. So I think that this should give you a pretty good shot at this exam. And we also, I'll put up the previous review session, which between me and you is probably very similar to this, but nonetheless, I'll put it up. And you also have the class reviews. So I think analysis of variance particularly is particularly good. So that one, there's another example of using SPSS to do an analysis of variance there. And I'm sure we did some other, in the other videos, we did some work with the Ttest, various versions of the Ttest. So you might want to go back, take a look at that, and check out any of the PowerPoints or some of the other notes and so on, because it might help you with some interpretation questions on the exam. So the exam, you have 2 shots at the exam. You have 3 hours to complete it in one sitting. At the end of 3 hours, if you haven't hit submit, it will submit on its own. You can save your answers. Don't hit submit until you're ready to quit the exam. You have 2 shots at it. Just remember that when you go to take the second shot, it's not going to remember your answers from the first. So you might want to make some notes, because at the end of the first test, you will see which answers that you got. You will be able to see in the grading if you click on the grade. It should show you which answers you got wrong. Won't give you the answers, just tell you which ones you got wrong. So when you go back again, you can maybe do a little bit more experimenting, go back over video too, and then maybe be better prepared for the exam.